Looks like we've got a fantastic attendance today, and I appreciate everybody taking their time this time of day to come and hang out with us and listen to our introduction to HPC Bunya. So I'm Jake. I'm the CTO of the Research Computing Centre at UQ. We've got Shannon helping out, Shannon Lindsay, our amazing comms and marketing manager, who'll be looking after the chat, fielding questions and things for us there. Plenty of people. Hopefully have some good questions at the end. So I think it's best we just get stuck into it. First, an acknowledgement of country. The University of Queensland acknowledges the traditional owners and their custodianship of the lands on which we meet. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connection to this country. We recognise the valuable contributions to the Australian and global society. Importantly and specific here, the planning and the design and the deployment of Bunya, this supercomputer, actually takes place on the land of the Jagera, Turrbal and Agorapal people. The name Bunya is partly in dialect, but it comes from the language of the Turrbal people itself. So today, what are we going to talk about today? Well, first and foremost, the what and the why of Bunya. What is a supercomputer? That might be a redundant question to some, but I think it's important to address. Why did we build Bunya and why did UQ decide to take this path? We'll talk about the technical details of the machine and the components and some of the design decisions and implications that we've made. Okay, so how to make the most of the system, which is incredibly important for researchers who want to dig in and get the most out of it, and how we get the value, but also at the end we'll have time for questions. Really important you put your questions in the Zoom chat so that we can go back, reference them and answer them one by one for you, and we can do a bit of back and forth that way. So what today is not, okay? It's not a deep dive in parallel programming. We're not going to get into that. It's not about deep optimization. It's not about topology or topology awareness of your processes. It's not debug. It's not the scheduler semantics. It's not silicon design futures. There's plenty of time for that. And we love that stuff. We live and breathe and eat those things. We're here to help on all that as the machine comes to life and as you start consuming and using it. But that's not what today is about, okay? So the what and the why, we'll get into the what first. What is Bunya? Well, it's a supercomputer. It's a phased deployment machine, and it's a heterogeneous tier 2 supercomputer, and it's made from commodity components. To unpack that a little bit, we use the term heterogeneous, meaning that it can be made of dissimilar components. It's not necessarily all identical. In part, and that is very deliberate, and that is a supported function these days of machines that are, I guess, a little bit more in commodity. They're not so specialized in the way the market has moved, and we'll get into that a little bit later. It's a very important feature. So what makes a supercomputer these days? What makes a supercomputer? Well, the bandwidth available to each node and the storage. We talk about MPS, or messages per second rates. We talk about latency of communication between nodes. Network topology, incredibly important. The potential for parallelism in a system. Floating point operations per second. Density, as in how much of a component can exist in any given node. Physical things, so cooling, power, how large the thing is. And generally, and this is a very coverall term, the powerful, ubiquitous tools that are now a critical part of scientific research, any research infrastructure. So it's an extension and an enabler to us and our scientific instruments that generate data so that we can learn things. We take data and we turn it into information. Okay. So with that, we'll talk a little bit about why we built Bunya. Okay. So there is a bit of philosophy to this. And I think it's something that bears a little bit of, I guess, work and thought and a little bit of dialogue on. So we needed to replace our old supercomputers, FlashLite, Tinaroo, and Awoonga. Technology has moved on. We don't really need, or we perceive that we don't need separate supercomputers to do specific jobs anymore, okay? It's time gone by where we had separate use cases for separate machines, and we had focus areas for each machine. Good examples of that were FlashLite as a high throughput, high memory machine. We had the Venus supercomputer, which is still a current machine. That's our newest super, which is a GPU dedicated machine. And we had Tinaroo, which was a more kind of commodity mixed MPI type machine. And those things all lived under different buckets and different roofs. We don't think that paradigm holds true anymore in the same way. We think that we can do these things under one roof now. So commodity has changed this industry over time. There is still room for this, and I'm not going to say that it doesn't exist, as there are highly specialized systems out there, but we think that given the commodity and scale that can be achieved in the x86 market, coupled with, I guess, the renaissance of silicon and the way things are happening, there's this big advantage in layered upgrades of components which are easily and readily available, modulo the complexities of what the pandemic and the era of silicon demand have created. So the other big thing about why we're building Bunya the way we are, which is a layered progressive approach and, you know, in tranches, is to put regular performance improvements in the hands of our people, right, in our researchers. We want to provide access to fast, cutting edge things in step change kind of performance type arrangements on a regular basis, not every few years if we're lucky. You know, we want to be able to do these things on a regular basis so that people can feel the impact and they get a bigger impact every time, and it happens more often, not little bit by little bit over a very, very, very long period of time, but often instead. The other thing is smarter partnerships with our vendors. We'll get into a little bit of that later, but it's about having a tighter knit group of vendor capability, and they're stronger and they're enabling, not spread so wide and so complex that we don't have a good strong niche knitting anymore. So this is about being a little bit smarter with this kind of thing and creating efficiencies in that as well, procurement. So there's a thing about decision supremacy here and agility in an unstable world. Now that's complicated. I'll unpack that. It's about not putting too much into one thing and going, this particular chip or this particular technology is perfect and we should sink everything into this. We should go hard on this particular thing. This is about being able to move quickly and change your mind as research dictates it, or the market dictates it, or things change, right? So it's about not digging in too deep on one particular fixation of a technology. We're building in a way that allows us to do that, and we're tooling up in a way that allows us to do that. So everything under one roof. Up until now, we've had multiple machines to submit to, different methodologies for different machines in some ways. We've shared some things between them, but we've had separate systems to do separate jobs. And, you know, from our perspective, there's an administrative overhead in research to enable that, which we don't want for our people. We want people to have a really easy, fluid experience. And in that regard, we want to be able to offer it under one roof. So there's no more steps to determine which supercomputer to use. You just ask Bunya for the right resources in the right petition, in the right quaz, or the right Slurm queue, right? So this is about simplifying processes for us as well. We want things to be less bespoke in some respects. The way we're building, which the team are doing a fantastic job on, is more hyperscale-like, and it's more infrastructure as code-driven. And that is how we would like to roll from now on. We'll get into a little bit of that later about some of the design ethic. On the schedule, this is important to some people. We are probably turning off FlashLite in the coming months after Bunya enters full production. The same could be said of the second phase of Bunya deployment. We'll be turning off Tinaroo. Okay, so to make sure people aren't spooked or concerned or worried about that, we are making sure we are rolling up capacity, rolling up capability on Bunya before we get rid of our other supercomputers. So there'll be some phasing. There'll be some phasing as well. This isn't a turn off, turn on, or turn on, turn off kind of thing. There'll be phased approaches to get everybody from side A to side B. but we're making sure that we've got enough capacity to withstand these things. So some commentary on our approach in how we're building. It is from the ground up approach, okay? What does that mean? It's not a turnkey solution. It was never our intention here to build a machine that was coming straight out of the door, push a button and turn it on and it just works. That's not the approach we decided to take, okay? Different people have different opinions about the efficiency of that. But our opinion was we knew what we wanted to do. We had a very clear vision in mind of how we would lay the machine out and what we would do. And to that end, we didn't feel that a machine that kind of came wrapped in a piece of plastic was necessarily the right approach for us. So very deliberately, we went through a very robust and long procurement process to find a partner that we could trust, someone with the right balance of capability and value, delivery capability as well, which is really important, technology prowess, very strong roadmaps, and willingness to work hard with us long term. No secret, that's Dell Technologies. And in this case, we find that that has been the right alignment for this undertaking. So we've constructed our own software ecosystem to manage our supercomputer, okay? That alone is a significant task. Some will suggest that we should not have bothered and that we should have taken things that already existed in common off-the-shelf software. We're kind of doing that anyway in the open source field. We're leveraging things and frameworks and technologies that exist. But the way we saw the world and the things that we looked at and the things that we like, the things that we don't like in the management of supercomputers, we thought we can put together something that best suits our needs and best suits our users. And we can add our own little bits of innovation to this so that we've got a truly infrastructure as code composable machine in a way that suits our ecosystem and our users best. So we built our own HPC management architecture as well. We formed our own doctrine in the way that we will assemble and build the machine. We have some slides coming up that explain some of that in what we're doing at a very high level. Importantly, yeah, this is modern day commodity computing at a large scale, but it's a real grassroots effort. I think I'm quite proud of what the team are putting together. I like that we're doing this in sort of a humble way that is not grandiose. It's by us. It's how we would like to make it work for people. We think we'll get a good balance of things for people this way. And it feels right that we're doing something in a bit of a homebrew way. None of us want more work to do than you know, we have hands and legs and arms to do. We think we're going to strike the balance well. And in the end, the way we tool this machine up and the things we build and the orchestration that we put in place actually may aid us in administrative overhead and burden us. We're quite pleased with what we've done so far in that regard. So let's talk about the technical details of Bunya. So some of you will be rubbing your hands together and cool, the good stuff. Hardware first. So on the surface, we have 3 node types. Okay. So there is a standard node. That standard node is a 1RU Dell PowerEdge R6525. We have a high memory node, which looks suspiciously like the normal memory node or the standard node, albeit memory difference in density, which is a 1RU node. And we have some Explorer nodes, which we'll get into a little bit later, which are a 2RU Dell PowerEdge R7525. The reason they are a higher density node or a higher RU node is because we have to fit the GPUs physically in them. So that's the building blocks of Bunya. Okay, they are the bread and butter or the compute engines of this system, nodes. For those interested, and I know there are people out there watching who are interested in this kind of thing, we have a 1RU node here. This is either the high memory or the standard. You can see the CPU sockets, you can see the DIMM module layouts, the riser layouts, vectorized air cooling layouts from the Dell standard issue designs. These units are impeccably flexible in what they can do, the things you can load into them, and the configuration options are a baffling array of different capabilities. And this is how we're shipping things, and this is what we're putting into racks right now as the standard compute engine or the high memory node version. So you can see we've got quite a bit of DIMM density across the sockets. 2RU nodes look a little bit different. Their DIMM layout looks slightly different. Their riser config looks slightly different. Power config is slightly different. And that's to facilitate bigger risers, more cards, more interfaces and things like that. They're incredibly modular devices, fan trays and whatnot, pop out, pop in. In my time wandering around data centers, it's kind of amazing just how quick you can flip these things together and pick them apart and put them back together when you've got a down node or whatever. They're highly, highly maintainable. So moving along, we'll talk a little bit about what's in the nodes. So first and foremost, there's 60 of these in the standard nodes. So the CPU, which a lot of people care about, we have the AMD EPYC Milan CPU, 2 sockets worth in each node, 48 physical hardware cores per socket, 96 per node physical cores. For those interested in this kind of thing, I think at this stage, and my team will tell me otherwise if they feel appropriate, it's unlikely we will turn on hyper-threading. Generally speaking, there's debate in the academic community and the benchmarking community about this kind of thing, depending upon the codes, depending on how you characterize threads. It's not generally best practice to turn on HT or the multiple threads per core in HPC. There are use cases where it's shown to and proven to work, but it is unlikely we will turn it on. 2.3 gigahertz clock and a 3.6 gigahertz boost on this particular CPU. Gen 4 native, Gen 4 PCIe interconnect everywhere on the die, and that facilitates the impressive I/O and throughput credentials of these nodes. So the DRAM and the main memory on the standard nodes is 2 terabytes of memory at 3200 megahertz per node. And the network is an HDR InfiniBand RDMA interconnect from NVIDIA. Okay. And that is how we get things in and out of each node. Storage on board, it's just boot. So we have made deliberate choices here. We are not trying to load up flash memory or non-volatile memory type architectures onto the node. We're keeping it off node, and we'll explain some of that decision making later. And that is just boot. So for high memory nodes, we've got 3 of those in the R6525 series nodes, and they are identical to a standard node, except we've put 4 terabytes of memory into these nodes. They are special use cases where compute workload absolutely cannot fit into 2T, okay? The big sticker on the front, please don't ask for these if you don't need them. They are special and they are going to become incredibly useful friends to a very significant piece of our community, but we don't think they're going to be used in common parlance in everyday life, given that our standard compute nodes alone contain 2 terabytes of memory per node. So taking things a little bit further, the discovery nodes that we have available come in the Dell R7525. They're a discovery node from Dell and AMD. Dell and AMD have worked with us to provide these special early access use case type technologies. These nodes are not part of a dedicated build out yet. These are discovery and explorer type technologies. Our dedicated GPU phase for Bunya is going to come in our next tranche, most likely in our accelerated tranche of this supercomputer. So they're identical to a standard node, except we have a little bit less RAM. We've only got half a terabyte of memory, same memory clock, but we have 2 of these MI2 10 Instinct GPUs in each node. Each of those cards in each node has 6,656 stream processor cores. It's not an NVIDIA GPU. I get that goes without saying, but I think it's very important to underscore to people, if you're coming at these nodes or asking for access to these nodes expecting CUDA, this is not a CUDA GPU, okay? This is ROCm, this is HIP, this is a different technology entirely. This is new, this is different. It has different performance factors that will, I guess, make themselves known when we start to really get into this. We've already got an interesting community of users who are engaged and are keen to get involved with these types of nodes, and they've already got proof of life in running on AMD's GPUs. So we're very, very welcoming of the community who are engaged with us already, who are getting involved. So we'll talk about the network and the cluster interconnect a little. We are using an NVIDIA HDR InfiniBand QM8700 quantum switch. Used to be called, I think, ConnectX, and well, ConnectX is the HCA, but it used to be called Connect or Connect Switch 2 or Switch 2 or Connect IB. So the 200 gig switches sit atop the racks there. We have the ConnectX 6 HDR interconnect that then connects to the node directly over a PCIe Gen 4 bus at 32 gigabytes per second on a 16 by lane. Okay. So that facilitates and is a significant part behind why we don't use Ethernet. We use InfiniBand networks. TCP overheads are too high, latency is too high. InfiniBand is how we glue everything together from storage and share memory, share processes, and how we get messages from node to node. So each port connects at 200 gigabits per second to each switch and to each node. Each port is an RDMA port, verbs bypassing the TCP stack entirely in this particular case. And we've got about point-to-point latency of about 130 nanoseconds. So as generations of Mellanox hardware have progressed, they've managed to push down latency further and further and further. At some point, physics gets in the way, but we're hovering around 130 nanoseconds point-to-point. Around 200 million messages per second can pass through the card, which is quite useful for the purposes of very high throughput computing. Blocking factor. Lots of people ask questions about blocking factor, and we have opted for some blocking factor, and that will be explained a little bit later. So to some people, that's quite contentious. To us, it's not, okay? And I'll explain why. So getting on to storage. Scratch, Scratch 2, and some new flash options. So Bunya focuses on high-speed Scratch storage external and off-board rather than local storage on the compute node. Users of FlashLite may recall that we packed a lot of storage onto the local node. We have chosen, in this case, not to do that. Okay. So there are good reasons for that, and we will get into a little bit of that. But in this case, yeah, we turned on the current version of Scratch in May 2021. That technology continues with Bunya, as it is really quite new. So that is the IBM Spectrum Scale GPFS ESS 5000 type arrays. So it's capable of around 80 to about 100 gigabytes a second of throughput, give or take what block size and sector sizes the transfers are being used. Hundreds of thousands of IOPS, input-output operations per second. It's a very fast array. It's serving us quite well so far. So the performance of that particular array was never really realized when we put it in. And that's because the current supercomputers that were in place at the time were not capable of reaching those speeds. They couldn't hit anything beyond 56 gigabits per second of their interconnect on any given node. And in aggregate, they were not getting out there that far anyway because of the inefficiency of some of the switching and the network topology we had in place at the time. So Bunya will start to actually really take more advantage of the storage that we've got off board for Scratch. Things that excite people, we have Scratch 2, which we don't talk about too often, which is an all NVMe flash file system, still GPFS, still parallel file system, Spectrum Scale, made for specific I/O and latency sensitive codes. It's limited in its capacity and it's accessible by specific request and assessment. Your codes have to demand something incredibly special to warrant using this particular piece of our storage infrastructure. There are use cases, but we have to work through it with you, and we have to be able to demonstrate that it's a good use case before we say, yep, go and use that crazy flash. We're also working on, in the planning phase, of a further generation of all flash scratch options for Bunya. And that is all about pushing that really high IOPS, very low latency paradigm even further. It's perhaps something not seen in any current supercomputers in Australia. Time will tell how that pans out. We're not there yet. As I've carefully stated there, very much in the planning phase of that particular option. So the technical details in aggregate. This machine has 6,048 physical CPU cores, lots of threads. Whether we exercise them or not is debatable. In our GPU Explorer nodes, over 26,000 GPU stream processor cores, 132 terabytes of memory across the nodes, 12.6 terabits per second of blocking bandwidth accumulated through all the nodes. So now we'll get on to something a little bit deeper, and we'll talk about the component choices we've made. There are people who are probably quite interested in why we have made the choices we've made about these components and the way we built it. Part of it is the legacy of FlashLite. So FlashLite came out of the mind of the director of the Research Computing Centre, David Abramson. And David's vision for it was a high throughput machine, very memory rich, very flash rich. And it was modeled in part from another visionary machine overseas. It was ahead of its time in terms of its intent and its density of memory and capability and NVMe. It was kind of special at the time. FlashLite was ahead of its time in that people really only got the hang of it towards nearing the end of its life, and they really took advantage of it. But because of that legacy, what's happened is this community around it has kind of formed. So life sciences and bioinformatics communities at UQ that use this machine and use our facilities, RCC's facilities, really implied that a memory-rich requirement was important. No one at any point came to say, you must. But given what we saw happening in the way FlashLite was being used, we thought, well, we can't take a system away and not give something equal to or much better back. Fortunately for us, in what Dell Technologies are providing us, we've been able to really give back in the density of memory per node. We've been able to really, really give back. So we're continuing that legacy in collapsing FlashLite's workloads into this machine, and we're going to be able to do even better. So we really wanted a strong core to memory ratio. We wanted over 20 gigabytes per core. And there were people out there that said, geez, it would be really nice to have that much memory per core to be able to do certain things. The other aspect was to offer, really high throughput per node. So 200 gig per second per node, it's making sense given the proliferation of incredibly data-intensive workflows. This isn't a surprise to anybody running a supercomputing center at the moment, I don't think. Our Milan series CPUs plus GPUs all benchmark well over these kinds of rates in terms of being able to pull and push things out of a node over an IB interface. We can get 20 gigabytes a second into a node easily, right? So we must be putting those kinds of throughput credentials in a system. So the future fight is now. Hyper data intensive workflows are here. AI and ML training is aggressive. It gets talked about, in my opinion, a little bit too much. It's not the only game in town. There's a lot more going on. Not everybody is an AI and ML researcher pulling in a big data set. There's a lot more data intensive workflows happening. But when you see terabyte data sets in memory per task, you think, yeah, okay, we've got to cater for this. And that's part of why we've done it. Memory bandwidth per core is really important to us. We didn't use 64 cores per CPU as some entities will, for good reason for them as well. But for us, we found some interesting analysis and showed some unwanted granular bandwidth per core effects. So there's a very nice balance here that's been met, and it's given us the right kind of skew to get where we wanted to without detriment on either side. The legacy of Tinaroo is important too, that more commodity, but also more MPI focused. We realized though that investing too much in the interconnect was of limited value for us. So when you've got so many thousands of cores that can be within one hop of each other or on the same switch in the same root complex, in a single rack for an MPI rank or a co-location, we thought, hang on a second, if we go too heavily on all-to-all communication, we might actually be doing ourselves a disservice. So we sacrificed all-to-all zero blocking for the sake of many cores and getting more cores and more density and more memory. So people will then say, oh, but what about your storage blocking? Well, our characterization of our storage I/O patterns would suggest to us, cautiously, that it's going to have minimal detrimental effect. Okay, so we believe we'll probably get our cake and eat it too, and we think that the researchers and our users are going to be quite happy with it. Time will tell. We've built an architecture efficient to duck and weave if we need to change that. But at this stage, we're fairly confident that this was the right approach. So software, Slurm. So Bunya will use Slurm. It will use Slurm. The community, evidently, would appear to have voted on next generation systems using Slurm. Okay. We don't dislike PBS. We don't have a problem with PBS. It's just we seem to see general trends in industry and doing the kinds of things we specifically do. Everybody's pointing at Slurm. So it's good for our use cases and our accelerators. So we'll use fair share queuing on Slurm. We'll implement priorities, weighting adjustments. We'll probably put preemption queues in and quads for different balance and allocation purposes. There's a lot to that. Scheduler strategy and scheduler design is a dark art. At the end of the day, we want to make it most fair and most useful for all of our users. So we'll patch our Slurms during our schedule maintenance windows to bring features and fixes. Anybody who's close enough to the community will know that there was recently a CVE associated with Slurm, highlighted the importance of patching your scheduler regularly and often. So we'll be responsible for managing the different hardware types in this heterogeneous system. Schedulers are that good these days that we can absolutely do that. So we'll use different partitions in Slurm and different GRES types to point at the right components of the supercomputer. This isn't unfamiliar to users of the Vena supercomputer. You'll be familiar with the GRES types on that for different GPU types within the supercomputer itself. So we keep it all under one roof, but we give you the ease of use of knowing that you can be to that one machine and just change your GRES item to target the correct GPU. So just for those who've never touched Slurm before, this is a great slide from Dr. David Green. He uses this slide in training runs. It just talks a little bit about how you would do it on Slurm versus how you would do it on PBS. I promise it doesn't hurt. These things are actually really easy to transfer and change. On software, we are going to run with Rocky Linux in the initial. Okay, so Rocky for us, I think it seems to feel right at the moment on a start of 8.6, if that's where we land. Why? The community seems to be supporting it. There seems to be general widespread support and acceptance for Rocky. I'm not hearing any detractors from that so far. It's equivalent to other Red Hat releases and where CentOS left off. Okay. Reality, the way we're building the system out and the things that we're doing in a modular way, it shouldn't matter too much what the base OS is for our users. And that's the experience that we want for our users. If we decide to change later, the way we go about this will be mostly transparent to users. We've done interesting things with modular imaging in the past. I think it was an interesting foray into a different way of imaging, but it proved not as flexible as we would like. So we are learning from that, and we are doing things differently now so that we get a better user outcome, a better usability, and better maintainability overall. So let's talk a little bit about packages, software, libraries. Probably won't be too many surprises in here. We'll use modules, just like all the other systems we built, just like many of the supercomputers across our country and the world. A little bit about modules there if you're interested. So the same simplicity to load out all the tools you'll need. Hopefully this time with a little more consistency. There are practices around modules. There are practices to be had in the way we do dependency calculation in modules and things. We'd like to clean it up a little bit, make it even easier. So it'll have a very familiar software catalog. Dr. Marlies Hankel has been doing a fantastic job of getting out there and getting the user community engaged to figure out what packages people want. So we went out there and actually built a whole survey to ask what people wanted and what their expectations were to begin with. No surprises in things people want most. So we've actually got stats on the requests so far. UQ users and partners, if you haven't already, please fill out the HPC software survey. Just that link will probably be there for a while. I've shortened the URL. This is useful just so that we can gather what your expectations are. So the libraries will be what you'd expect. There's no surprises. The Open NPI, the Intel NPI, all the usual compiler tool chains, and on top of that, the AMD specific tool chains, the AMD compiler, ROCm, HIP for GPU type workloads. I don't think there'll be anything that will stick out as unusual or strange. We would like to add further things in the future as required. So we expect our users to be pretty vocal about the requirements. We would like to think that people will be submitting support requests for codes that they want to see in the system. I haven't seen a situation where people don't ask. So deployment. This bit is more about us and our methodology, but I think it's important to explain our intent. So continuous integration, continuous deployment is a key feature of this machine. What does it look like? Well, you can oversimplify it and say it's build, test, merge, and then throw into the repository and then automatically deploy to production. The stacks we'll use include Salt, the Salt stack, Gerrit, and Jenkins. Okay, so the team are working really, really hard to get all of this tooling up and running. It has a couple of effects. So this is our new command and control tower, really. This is how we're deploying. There are plenty of really good tools in industry available, bundled up, commercially sound, which you can buy off the shelf to do all your management for you. None of it really hit the mark for us. It didn't do exactly what we wanted to do. So the way we're doing things, and there's another link if you're interested in what CI/CD is, and it means different things to different people. But for us, it means an ability to get code up and out, tested on the system, smoke tested really quickly and functional, and also repeatable, destructible, and rebuildable is really important. So that's a big part of our ethos, and it really is about pull down and bring up fast. It's about repeatability. It's also partly a social thing. There's a piece of, I think there's a part of it's a social thing in the way we actually have participation from our other admins in the supercomputing sphere around us, and it will give people stronger input and ability to get code on this machine running quicker in a sensible and verified way. And to that effect, cybersecurity principles we baked in from the beginning, not after the fact, right? We'll be doing some interesting things in the pipelines to make sure that we're doing things right. Code is verified. Code is not just assumed to be fine. So we'll talk a little bit about security and auth. So we live in a little bit of a different world now from when we built our previous supercomputers. Things change quickly. I think we're all very mindful of how our world looks now in terms of cyber threats, exploits as a consequence of connectedness. So we need to take really appropriate measures to keep research and researchers safe. Supercomputers are really attractive things. They're significant targets for a number of very good reasons. So, it's not an access by default supercomputer. Users can apply, as our users do, to RCC staff who will take you through an onboarding procedure. We've got a going form available so that people can go through that process. It isn't a default, you have access by design kind of thing. So how are we going to do auth? Well, we won't talk too much about this because that, I guess, would be disclosing the nature of security, but we'll be leveraging UQ authentication for UQ researchers. we'll be leveraging Chris Cloud QCIF LDAP for researchers from other institutions and partners. And that's a really lovely balance that we can create here. We'll be locally caching LDAP infrastructure so that we've got fast lookups, and it will be born with MFA. Okay, so for those not clear on MFA, multi-factor authentication. This is not a thing where you type your password and that's good enough. Okay, there's more to it. The premise has to be stronger. Our posture has to be stronger. So it will be born that way. Monitoring metrics and reporting. So this is good stuff that is both, or will be both user-facing and for us. So these wonderful tools, Grafana, Prometheus, and Victoria Metrics. So we're putting a lot of renewed focus on user visibility and granularity of reporting. We feel internally we haven't done enough over a long period of time to give people back that visibility, and we want to do more for people. Slowly but surely, it bubbles up that people are asking more of their metrics to understand their jobs, to understand their consumption more, and we feel it's time that we put effort into that. So Sarah has given us some great words here on what Prometheus is doing, how the node exporter works, how we're scraping, and we get things into Prometheus compatible interfaces into Grafana so that you can then display stuff. So this provides graphs and dashboards. It gives us a nice overview of our systems. So we're going to do central stored logs for viewing Grafana as well. So in the future, our future state, hopefully by the end of the year, maybe sooner if we're lucky, will be a public-facing set of dashboards and metrics for improved usability. Hopefully, we'll expand out to further RCC services as well, aiming to give really rich information out to the users that require it so they can better understand the nature of their jobs, their workload, overall capacity and utilization of their stuff. So getting to the back end of the talk, making the most of Bunya. How do we make the most of this system? Well, we're delivering the AMD EPIC CPUs to begin with. So this is different from our 4 previous machines, which were Intel systems. So for many people, it probably won't make that much difference flipping from Intel to AMD. Okay, so it's another x86 64 CPU, just much more powerful. For some of you, optimization is of the essence. Okay, so consider using a different compiler. Consider the AOCC. Look into AMD's different options. Okay, GCC is cool. GCC has lots of good flags. AMD can take it a step further. Generate your instructions differently. Use some of the machine arch flags that are available. There's similar options in the GCC compiler as well, by the way. This is a very, very high level compile time optimization table that gives you some perspective. Okay. So there's a lot going on here. As I said, this talk is not deep optimization. Plenty to talk about here in time. We can have a great time with this stuff. And for advanced math, and there is some really interesting stuff to speak of here, we can get into that too. Okay. Again, not the topic of this talk, just a high-level overview. These are the breadcrumbs. So these systems are NUMA cell-based systems. The processors here are carved into sets of CCDs, which give you different NUMA domains. That's very important when you consider memory locality inside the system. It might mean that your systems work a little bit differently in terms of memory management when you throw your codes onto these CPUs. So we have a 48-core Milan chip. I think we've told you that. It looks roughly like that. If you're really, really interested in ripping the lid off one of these things, I don't recommend it. So you need to be aware that we're in the chiplet era now. This isn't a single core anymore. These are chiplets on top of a die, okay? So the arrangement is a little bit different in the way the cache sits around the chip. It exposes each as a NUMA cell. So there's plenty of connectivity between each socket in a board, right? But where your memory, and this is how it's different to an Intel chip, right? The Intel UltraPath interconnects look a little bit different to the way things were designed before. Up until that point, there was no chiplet design. That is changing with Intel as well. But it's a little bit of a different thing to get your head around in terms of memory management. To some of you, this will matter. I did my best here to make a diagram that sort of explains how these things connect together. What you're seeing there is one chip, one specific socket worth of CPU cores and 4 dies, all laced together with AMD's Infinity Fabric. Okay, and it gives you some perspective on the way things are connected inside a CPU these days. We can have fun conversations now about the implications of that, but that's the topic of an entire talk. So numeral awareness and applications, well, they should be explicitly numeral aware to take most advantage. Okay. Good news, many apps already are. Many things that are being compiled already are. GROMACS, actually, I was talking to a friend the other day about GROMACS. GROMACS comes up a lot in the office. Marlies and I talk a lot about GROMACS. It was ported natively to understand the earlier EPIC models. So this is all stuff that's already been done. It's already been thought about, right? And we're seeing, commensurate performance improvements as a consequence. OpenMP is aware, right? So there's considerations the way the OS itself distributes. That's something to be considered. Reality, many users, it's going to be inconsequential. It's going to be near enough is good enough. We love optimization. We love those things, but for many users, it's going to be fine as it is. How will your codes run? Well, after everything's said and done, for the most part, you can expect improvements without too much effort. Faster cores, more cache, faster interconnects, better path and branch prediction technology in the CPUs. Things have come a long way. Special cases, yes, there will be. It's unlikely to be the case. It's not impossible that you'll see degradation. Let's be fair, let's be honest. It's a whole change of chip, right? There could be something unique to your code that's happening in the code path that you've put it into in the compile from a previous generation of processor that does not work well. So maybe it goes without saying, but recompiling your code for a new CPU is a really good idea. Really, really sensible, pragmatic, normal, sensible, again, idea. There's a lower chance of things going wrong if you do this. Don't expect major gains if you try to run code that was compiled on 7 architectures ago of a different chip in a different era, okay? It might work terribly, okay? Some common sense and pragmatism is required. I want to acknowledge the people that have made this happen. I want to acknowledge Sarah Walters. I want to acknowledge Dr. Marley Sankel, Dr. David Green, Ashley Wright, Eric, and Owen. They are all working incredibly hard to bring this system together for our researchers, and I think it's a labor of a lifetime. Some of us have built multiple supercomputers. We've had the fortune or the pleasure of building multiple supercomputers, and I am so fortunate and privileged to have such an amazing group of people to work with. They are the true superpower behind this. They're all brilliant stars. So special thanks. So to our RCC director, Professor David Abramson, the man, the originator, our supporter, our ultimate innovator, our adventurer, and our luminary. The guy's one of a kind. So the UQCIO, Rowan Salt. Rowan is awesome. He is our support, he's our carriage and our enablement, and he understands what we're doing. And that is really important. We are very fortunate enough to have a CIO that gets what we do, right? So the local and the global Dell team, Jules, Brett, Kat, honestly, I can't thank you enough for how hard you have worked with us, for us. You are tireless, you are problem solvers, you are tenacious, you are pragmatic people in a very complicated time to be alive in computing. And without you, we would just not have gotten this far. So we really appreciate the partnership and the effort you've put in here for us. It doesn't look like a normal commodity game. It looks like you care, and that matters to us. So our users and our research groups, why we do what we do. That's why we get out of bed for these things. So with that, I'm going to say thank you, and I will open it up for questions. Oh no, we do have. Oh, we've got a question already. Okay, so timeline to deployment. We are hoping to see the system up in July. Okay, we are working hard to get the system up in July. Infrastructure is coming together now physically, and it is now a matter of software and pipelines. Okay, so I've got another question. So people are keen to understand, so this is from Gareth. Thank you, Gareth, that's a good question. Keen to understand the Homebrew management system. How far does it penetrate? Do we still get full support? Have we kind of asked, or have we engaged someone from support for contractor going alone? Okay. So support in and of itself here is not around hardware infrastructure. That's all taken care of. So the complicated aspects of hardcore support for the infrastructure from a machine perspective and a physical perspective are all taken care of by our partner, Dell Technologies. Okay. The Homebrew management system is not particularly uncommon in so much as we are just building out the deployment of the infrastructure ourselves using open source technologies, whether it be the Salt Stack, whether it be things like, I suppose, the Pixie booting technologies and whatnot. They're all quite commodity things. So it goes down to imaging the metal, and we lay the operating system on top of that. I think what you'll find is, in most part, if you're running Rocky Linux on a supercomputer, unless you've gone and paid a third party to support your operating system, it's kind of situation normal or status quo that we would simply be supporting the operating system on top of that. Okay. Ben had a question. So I see some questions in the chat. Sorry, there's lots coming through now. So I see one from Toby O'Brien. Toby. He says, so the system is heterogeneous. How far does this go? Are you tied to AMD now in the future nodes? Good question. So I can answer that by saying that the way we're building out our software pipeline is that we will make it such that we can compile multiple architectures without any further overhead, and we'll be able to target the right arch for the right CPU and heterogeneously schedule. Not, oh, you've compiled for that particular arch, now you can't use that on that node. No, the idea being we target multiple arches when we compile. That's actually a good question, thank you. So other tools exist, things like SPAC, things like Easy Build to be able to facilitate that exact thing. So how much memory is on the AMD Instinct GPU? My team will correct me if I'm wrong. I'm pretty sure it's 64 gigs of HBM2E on each of those GPUs. Beanie from IMB asked that. Yes, it's more than the NVIDIA Volta. Yes, it's less than the NVIDIA A100. So it's 64 gigs, so it's somewhere in the middle. Ben asked, assume we're getting an email telling us how we can sign up to use Bunya. Well, if you're on the HPC list already, you'll be hearing about it. If you're not, you should get in contact with rcc-support at uq.edu.au to how you can get involved. Right, more questions. Let's see what else. Yes, okay, so Wayne Spagnol asks, are you using GPUs as pure compute or a mix of desktop and compute? That's a good question, and it's pertinent to a whole bunch of the community. The MI210 GPUs at this stage, I'll make the brave statement that it's likely that those particular GPUs will probably be running in compute-only mode. We have every plan and every intention in our next tranche of working on a mixture of both visualization type or viz and frame buffer type GPUs and hardcore compute GPUs. So there is a mix to be had here, and we are working to understand what our users' needs look like to do that. Already we're getting strong feedback from our CVL community, for example, from people like Farah in IMB, and our CMM people telling us what their expectations are as far as visualization and compute goes. Okay, so there's an ETA. There's a question from Sarah McClem. Do you have an ETA for when Tinaroo and Awoonga and FlashLite? Okay, well, first, Awoonga's gone already. Awoonga is long gone already. It was turned off. As I said, Tinaroo will be turned off once everything is up and running and we've actually got a clear path to our next tranche of capacity. We would like to think we'll be turning FlashLite off in fairly short order in an organized, phased way as soon as Bunya is up, okay? I guess I've got to be careful with my words there. We need to make an orderly stampede versus a quick shut it down, everything's gone now. We'll be doing something phased, but it will be once Bunya is up in full production. Okay. Paula asks, is Bunya only for UQ users? Okay. So Bunya is in most part a UQ system. In the vast majority, Bunya is a UQ system. QCIF, the Queensland Cyber Infrastructure Foundation, has funded a small part of Bunya for partners as well. So there is absolutely opportunity for partners to consume a portion of Bunya as well. Okay, it's very important. So there is a question here from Juan. Thanks, Jake and team. Will CUDA be supported in GPU nodes? To be decided. We are looking at all angles of the GPU market. We are considering all kinds of things in what GPUs will be part of these, part of the second build out. At this stage, we're testing things. We're trying to understand things. There's every possibility that we'll have a mixture of things in the end. We just don't know yet. So we will be driven by what the users, the community, and the research dictate to us, not what the silicon says. Okay. Is there a plan? So Jay asks, is there a plan for CVL desktops on the new machine? We are talking a lot about that. Okay, I'm glad you've asked that question. We think there is some room to collapse our CVL in a disparate version that's currently in VNA into this new system and keep it all under one roof. It's a good question. We're working towards something like that, yes. Okay. I think that if I haven't covered everything so far, I think that covers everything that's been asked so far. There's a lot going on. Thank you. There's a lot of questions. It's fantastic. And I thank everybody for their interest and their enthusiasm. It's, you know, it gives me a kick to see how many people are so interested in the system. If there's any further questions, now's the time. We've got a couple of minutes left, I guess. Will the visualization nodes be only for CVL? Good question, Romello. You know, it's to be determined. We haven't gone that far yet. We haven't made any, you know, dictatorial points about exactly what it'll be for yet. There's every opportunity that CVL will be a workhorse and a platform for certain tasks. We may see future visualization capability for others. I know what you're getting at. You're thinking about more of the different kinds of workloads that you run, unique to your OU. Happy to have that discussion. Happy to take input from you to learn about, you know, how we could make that work for you as well, potentially. Okay. All right. Cool. All right. Thank you, everybody, for your time. I appreciate I've kept everybody over their lunch hour, the magic of webinars. I will give you back some of your day now. And I look forward to the team and I sharing the stage and the progress of Go Live in production in the coming weeks. All right. Thank you so much. Everybody have a good day.